Hi, this is the second video for week 3 trigonometric functions. This is the second of 7 videos for week 3 and covers graphing trigonometric functions. These videos are intended to help you to work through the online content for week 3. We recommend that you watch this video with your pen and paper and pause at the relevant times to try the examples for yourself. Graphing trigonometric functions. So first we're looking at here, y is equal to sine of x. Here, so we can use our calculator work 3. We've got here our x and we notice here that it's in radians. So first thing we're going to do is put our calculator into radians. Shift, mode and 4 for radians. So we have the R to tell us it's radians. So 0, we press sine of 0 and we notice we get 0 here. That's a nice easy one here. So we've been started off here. We've got sine here of pi divided by 6. Sine of pi divided by 6 here, and we get 0.5. If we do the same thing, so pressing the across button to go back into our equation, and we can change our 6 into a 3, and equals, here we get 0.866 here, so that should be 87 for our 0.87. We're doing the same thing, pi divided by 2 here, and we end up with 1. So we keep on going, 2 pi divided by 3. So we adjust here, 2 pi divided by 3 and equals, and we get 0.87. So 5 pi divided by 6 here, and here we get 0.5, and now pi, we get 0. So we notice that these numbers are repeating, 0.5, 0.5, 0.8, 0.8 here, our 0, 0. Then we're going to have negative 0.5. We keep on going through with our, here we're going to have negative 0.87. We'll have negative 1, negative 0.87, negative 0.5, and then back to 0. So our sine curve, when we draw this here, here's our 0. We have pi on 2, pi, 3 pi on 2, and 2 pi here. Here at the top we have 1, here we have negative 1. So here at 0 we're on 0. At pi on 2 we're on 1. Here at pi we're on 0 again. 3 pi on 2 we're on negative 1. 2 pi we're back on 0. So we know here pi on 6. So here that's pi on 2, that would be pi on 4. So here's pi on 6 and here's pi on 3. Pi on 6 we're at about 0.5. And pi on 3 we're at 0.87, and so this gives us our sine curve like this. Yeah, and this repeats again and again every 2 pi. So drawing this up, we have our 0 here, so we'll say here's 0.5, here's 1. We know at pi on 6 we're at 0.5. Here, pi on 2 we know are at 1, pi on 3 we're at 0.86, so we're about here, and here, and through. And so our sine curve goes like this. And then same, here we're at negative 0.5, here we're at negative 1, negative 0.5 and 0, and we're at 0.87 here, and we go through like this. Okay, so here's our curve again, and we often draw it in our unit circle. So our 0, we're at 0. Here, at 1, pi on 2. Here, 0 at pi. Here, 1 at 3 pi on 2, so that was pi. And then back to 0 again at 2 pi. So it's just a different way of showing the same information. Same for our cosine curve here. So our cosine curve here, at 0, we're at 1. There's our 0 and negative 1. And then here, we go the whole way through our curve. Here, we're at 2 pi. At pi, we're at negative 1. Pi on 2, we're at 0, and 3 pi on 2 at 0. And we've drawn this curve so you can notice this curve just continues on infinitely in both directions. So if we put our sine curve in blue together with our cosine curve in red, so we can see that they're the same, just out of phase by pi on 2. So here, pi on 2 between them, pi on 2. They reach the same points, we just have pi on 2 between them there. So our sine and our cosine waves have many applications in engineering, both in electrical, mechanical, civil, robotic, and other disciplines. If the amplitude of a sine wave is increased, so we're increasing our amplitude, then we have a function such as y is equal to 2 sine x. So it's the same shape as sine x, but our vertical amplitude changes from -2 to +2. So our regular sine curve is like this at 1 and -1. We're multiplying it by 2. 1 multiplied by 2 gives us 2. -1 multiplied by 2 gives us -2 there. Okay, so the next function we look at is our tangent function here. We have our function of x is our tangent of x. And what we notice is this is quite a different curve. We have here these asymptotes. So we'll write this right down. We have these asymptotes. So here we approach but never touch them. So here we're approaching towards pi on 2, but we continue up here towards infinity and we never touch that line. We go this way and we continue to negative infinity and we never touch this asymptote line here. And we have these asymptotes at pi on 2, negative pi on 2. The next one will be up here at 3 pi on 2, and so on. And what we mean here, we have no solution. So tan of pi on 2 has no solution here. And if we think about here, our tan of theta is our sine of theta divided by our cosine of theta. So if we work through this, when our sine of theta is equal to 0, we have 0 divided by what our cosine of theta is. So our answer will be 0. So when sine of theta is 0, our tangent of theta is also equal to 0. When our cosine of theta is equal to 0. So here we're dividing by 0. And when our cosine of theta is 0, we have no solution for tan of theta. Oh, tan theta. So that is our points here where our asymptotes are. That is where our cosine of theta is equal to 0. So we notice with this we have a period of pi. For our sine and our cosine curves, remember here we had our period where we repeated of 2 pi between here. So these are our main parts here. Our tangent curve, similar to our other curves, repeats again and again. Repeat and repeat. Keeps on repeating all the way along. Here, so this is at 0 here. We pass through here at negative pi. We have pi on 2. Here we have pi. 3 pi on 2 and then 2 pi here. Okay, so now we're looking at an example with more curves here. So here we're looking, our function of x is equal to 1.5 times the sine of x. So what it is 1.5 times sine of x. So here we have in red our sine of x. So that's y is equal to sine of x. Our function of x is equal to 1.5 times that. So here at pi on 2, our sine of x is equal to 1. So here 1.5 times sine of x will be 1.5. Here where sine of x is equal to 0, this will also be 0. So all we're doing, we increase how tall it gets on each of these. So here for our sine curve at 3 pi on 2, we have -1. For 1.5 sine of x, we're going to be down here at -1.5 here. If we were to put another example in here, we had f of x is equal to 3 sine of x. It'd be exactly the same thing at pi on 2. We're going to be, that's 1.5, we're going to be up here at 3. So up to 3, through the 0 at the same point, and then down to 3, and continue on. So whatever number our trigonometric function is multiplied by is the amplitude of the trigonometric function. So here, 3 sine of x would have an amplitude of 3. A half sine of x would have an amplitude of a half here. So here we have our amplitude A, here where A sine of bx. So our A, our amplitude, is what we have out the front here, whatever we're multiplying our sine function by. Now we're looking at something slightly different. We're looking here, our function of x is equal to sine of 2x. So we're multiplying whatever our x is in here by 2 before we put it through our sine function. So here we want sine of 2x. And what happens here is our wavelength gets shorter here. Our period is shorter. So we have the same shape curve. This is our sine of x curve here. We have exactly the same shape, except we've squashed it. 2x means we've shortened here. Our period is now pi, whereas before it was 2 pi. So here, to use this, we see that it's narrower, period is pi. We can use this to find the period of other trigonometric functions. The number the trigonometric function is multiplied by divides the regular period 2 pi to find the period of this trigonometric function. So here, sine of 3x would have a period of 2 pi divided by 3. So we go in here, and sine of x divided by 2 would have a period here of a half. We write our period here as omega. So here omega is equal to 2 pi divided by our b, and we notice this is an absolute value. We don't care if it's positive or negative. And so here we have A, that was our amplitude, and bx, so that's here what we have in here, and we use this to find our period. So here we find our period 2 pi, which is our regular period here. So if we're working with a tangent, that would then be pi. But with a sine curve and a cosine curve, that is 2 pi. So here for sine and cosines and their reciprocals, they have a period of 2 pi. We use the absolute value of b because b may be negative. So here our omega is 2 pi. So if we have sine of 2x we looked at before, that's our b. This 2 is our b. So omega is equal to 2 pi divided by our absolute value of 2 becomes 2 pi on 2, there's no negatives, and is equal to pi, which is what we found on our previous page. For our tangent and cotangent curves, our regular period is pi. So our formula becomes omega is pi divided by absolute value of b, where a is equal, where we have a multiplied by tan of bt or bx. For our tangent and cotangents there. So the next type of thing we're looking at here, we're not multiplying our x, but we have here this pi here. We've got our function of x is sine of x plus pi. And so if we put this on here, here's our sine of x curve. Here is our sine of x plus pi. So we see that it's really very similar to sine of x. But here we see this one's been shifted over here. Here, this point's shifted over, this point is shifted over. Everything has been shifted here by pi. So it's been shifted by pi to the left. So here we're shifted to the left by pi. If the argument of the function is in the form of variable minus number, then the trigonometric function is shifted to the right by that number. So here we see we have plus, we shift our curve to the left. Minus, we shift our curve to the right. And we move it by that number. If that number's 1, we shift it by 1. If it's pi, we shift it by pi. So our trigonometric function shifted to the left by that number. So sine of x minus pi on 4 would be shifted to the right by pi on 4. And sine of x plus pi on 4 would be shifted to the left by pi on 4. So we're nearly finished with the different parts of the equation that we can be changing here. The next thing we look at, we have function of x is sine of x plus 1, and it's outside of our brackets. And so we could work out whatever our sine of x is, and then we add 1 to it. So here where sine of x is 0, we add 1 and sine of x is equal to 1. So all we're doing is shifting this up by this number here. So positive, we shift up. Negative, we shift down. So again, we said it's very similar for our function of x is equal to sine of x. However, this curve is shifted up by 1. If a number is added outside of the function, then the graph is shifted up by that number. If a number is subtracted, then we're shifted down by that number. So sine of x plus 3 is shifted up by 3. Sine of x minus 2 is shifted down by 2.